We have looked at the Bohr model of an atom, and we have looked at how electrons can be here and further out in these kind of orbits around it. Then we examined that they don't really travel in orbits. We don't have this simplistic model. We have a more complex reality, and we define regions in space where we have a high probability of finding that electron. We're going to kind of focus in on a hydrogen atom again for a little bit and get into some mathematical calculations associated with the spectrum that we get when we take that gas, apply energy, and see this splitting pattern that we have. So we're going to look at what happens when it lights up and be able to associate wavelengths of that light that's emitted with the energy of the electrons. Okay, so what happens when the light is produced, when you take a gas, put it in a chamber, and it glows? Well, what happens is the electrons smash into the atoms. The energy smashes into the atoms, electricity, which is electrons. And it causes the electrons within the hydrogen atom, for example, to be promoted up to a higher state. When an electron is promoted up to a higher state, it is promoted up to a higher N, L, and M sub L from where it was before. It's in some new orbital that's further away from the nucleus. That electron is not going to like having that high energy, and it's going to cascade back down and try to get back to a orbital that's in the n=1 area. So when it does that, it emits light that is just the right energy to jump those gaps, because it can't exist anywhere in between those. Remember, an electron can be in various allowed places, but it cannot be anywhere in between. So when it is in a higher energy and it wants to get to a lower energy, it has to get rid of energy, and it gets rid of energy in the form of a photon of light. Now, in the image on the screen there, it's kind of flattened out those energy levels, and they're calling them, they're just kind of plotting them out. Lower the energy, further down; higher energy, they move further and further up. But this state up here, we call it an excited state. Getting the electron back where it wants to be is called the ground state. Okay? And the ground state is when if you've got an atom with lots of electrons, where all the electrons are in their lowest possible energy state. Now, they can't all be in the n=1. The n=1 is like everybody in the campus living in one dorm room of that dormitory, okay? Because there's only, in this level, there's only one dormitory, and that dormitory only had one room. So you can't have everybody on campus living in that one if there's lots of people on campus. So the electrons will be in all of their possible lowest energy states, knowing that we have to move further and further away and make room for more and more people. All right, so here are the lines that are generated when in a hydrogen atom, where there's only very simplistic places that the electron can be. In the hydrogen atom, as the electron is being dropped back down, we have seen this image before. We see these various lines that are being produced of light. What we're going to be able to do is actually calculate those wavelengths, that 657 nanometers, that 486 nanometers, or any wavelength of any transition as an electron goes from any state down to any other state. In this diagram, they're all going to the n=2, and that gives us the visible region. It happens to be that falls in the visible region. But we could calculate it for any possible transition as an electron moves from a high to a low. So you'll notice here in the middle of this diagram the colored lines. We see the red, the green, the blue there. That's when an electron comes from some high state and lands in the n=2. It happens to fall in the visible region. But if it goes all the way down to the n=1, it's going to have to emit a photon with much higher energy, and that will fall outside of the visible region. Or if it drops down to the n=3, it will be outside. It's a lower energy, and it's also outside of the visible region. Okay? But this is what we need to know, and this is really a key statement here, so put a star by it. The energy transition, delta E, of the electron has to equal the energy of the photon. So I used h nu to represent the energy of a photon, because that's the equation that we use for calculating the energy of the photon. So let me see if I can write on the screen here. I don't know. Yeah, there's the pen. For just a moment. All right, so let's just examine one of these lines. As the electron goes from here down to here, it has a change in energy, okay? It has a delta E, final minus initial. So the energy, when it's at 1, that's final, let me put a 1 there, minus the energy of where it started, which was 3, is the delta E. And what this is saying, that the delta E of the electron has to equal the energy of the photon. Now that electron is going from a high energy to a low energy state. Its change in energy that we're going to put in here, well, let me say it this way. The energy of the photon has to be positive. So we'll worry about that sign in just a minute, okay? The other thing I want you to notice about what we see here is how those energy levels get closer and closer and closer together. For the hydrogen atom, we know that each one of these lines, the energy is determined with this equation. E equals minus R sub H 1 over N squared. That's how we figure out the energy of each one of these lines. When I do this one, it's 1 over 1 squared, all right, for this one. This one's 1 over 2 squared. This is 1 over 3 squared. A 1 over 3 squared is 9. The N equals 4 state is 1 over 16, 1 over 25. That difference keeps getting smaller and smaller and smaller as we move further and further away from that. All right, now, what is this? What this equation is the change in energy of the electron. If we take this previous equation here and we do energy final minus energy initial, we're going to get this equation. See, the F stands for final minus initial. Final minus initial. Energy final minus energy initial. We're seeing that play out here. So this gives me the change in energy of an electron. That's our Rydberg constant that I told you about before. This Rydberg constant will be provided for you at the bottom of the periodic table when you are doing your exam, so you won't have to have this memorized. Okay? This is where the electron lands when it's finished, and this is where the electron started with. So if the electron is going from a high state down to a low state, it is going to be a negative change in energy. If the electron started at a low state and goes to a high state, it will be a positive value for the change in energy. So the sign convention will play out with the way this equation is. Now, let's keep in mind something very important here. This equation only can be used when you're calculating the energy of a hydrogen atom. It cannot be used to calculate the energy for any other element. The hydrogen atom is very simplistic in that it has only one electron and that all the orbitals within these subshells have exactly the same energy. That's not true for any other element. In other elements, we're going to see that the S and the P subshell that are in this shell have actually different energies. But because of the simplicity of the hydrogen atom, it having only one electron, it makes for a nice simplistic equation. So we're going to learn to use this equation. All right. See the absolute value signs that I have displayed there? The photon has to always be a positive energy. The electron, as it goes down, is going to have a negative energy change. So a change can be negative. A photon can't have a negative energy. It either doesn't exist and there's no energy, or there's a photon and it has energy. So a photon always has to be positive, so we have those absolute value symbols around it. Now, what we know about the energy of a photon and about light in general are these two equations. We've learned about that. The energy of a photon is equal to h times the frequency of the light, and the c and the lambda nu are about the light. So our previous slide's equation is about the energy transition of the electron. Those equations on the right are about the energy of the photon that gets emitted. So with this, what we can do is we can calculate the wavelength and the frequency of the light emitted when a photon transitions between two states. So let's see if we can do this. We'll do this one together here. We have got an electron, and let me draw kind of an idea of what's happening here. Oh, let's just keep drawing on this one. So there's an n equals 3, an n equals 4, and an n equals 5. They get closer and closer as they move further away. We have an electron that was sitting here in the n equals 5 state, and it's going to transition down to then n equals 3. So that's the transition. When it does that, it has to get rid of one photon of light, just one, and that's that interchange between the electrons and photons. It's a one-to-one relationship. It throws out the extra energy it didn't want in order to land here. What I want to know about this eventually, but not yet, is I will want to know this photon's wavelength and frequency. Okay, I'm going to eventually do that. But the first thing I want to do here is figure out that electron's transition. How much energy did it lose? Well, here's the equation. It is in a hydrogen atom. It says so there. Okay, so this equation applies. Negative R sub H, that's the Rydberg constant for hydrogen, 1 over n final squared minus 1 over n initial squared. There's my equation. It gives me the energy of the photon. No, it does, but I don't want to say that yet. It gives me the change in energy of the electron. The electron is moving closer. It's losing energy. This will be a negative value if all's right with the world. Okay, it should be, because when an electron is going down, it's losing energy. That's a negative change. Okay, so we put our values in. Negative 2.18 times 10 to the negative 18 joules. That's the Rydberg constant's value. Where did it end up? It ended up in the n equals 3 state. So we'll square that. Where did it start? It started in the n equals 5 state, so we'll square that. This will give me the change in energy of the electron. It is a negative value, and it is a negative 1.55 times 10 to the negative 19 joules. Very tiny number. Okay, so that is the change in energy of the electron. Now, that's a change in energy of the electron. That's this energy gap from here to here. What we want to know is about this photon, the light that's emitted. What do we know about the energy of the photon? Well, on the previous slide, if you look back there, we know that the energy of the photon is the absolute value of the change in energy of the electron. So what is the energy of the photon? The energy of the photon is 1.55 times 10 to the minus 19 joules. Now, in a previous lesson and in your homework you have practiced this, you have learned to take the energy of a photon, and you know that if you know the energy, you can get the frequency and the wavelength of that light. So that is what you are going to do in our next slide, okay? So you're going to stop and you're going to do the work to try to figure out the frequency. Actually, this one is only asking for the wavelength, okay? So you're going to calculate the wavelength of that light that was emitted in order to do this, in order for that electron to drop down. All right, if you got E, you got the correct answer. If you did not get E, you probably already know what the correct answer is, but you might want to know, how do you do that? How did you get that? Well, let's see. If I know the energy of the photon, the first thing I have is this equation, E equals H times nu. I can get the frequency of that photon. If I know the frequency of the photon, I can use this guy to get the wavelength. So I'm going to use those two equations. Now, I might mathematically combine it since I really am not being asked for frequency. I could do the math on this one to give myself the equation E equals H c over lambda. Let me go ahead and do that just algebraically. How did I get that? I'm going to take, I want to know the wavelength. So what I'm going to do is I'm going to solve for frequency here. C over wavelength equals frequency. I'm going to plug this in right there, and that gives me this equation. Okay? So now I'm going to take this equation that I just don't like memorizing. I always derive it in my mind as I come to it. Or you could do this equation first, plug it into here, and solve for this. You know what? Let's not use that equation. You can plug and chug that equation. Let's just use these two equations right here. So what do we have? We have the energy of the photon. If we take the energy of the photon and divide by Planck's constant, we'll have the frequency. E's value was, absolute value is 1.55 times 10 to the minus 19 joules. We divide by Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, and that is going to give me the frequency of this light. Let's see if I have a value for that frequency. It is 2.384 times 10 to the minus 14. 2.34 times 10 to the negative, no, that can't be right, to positive 14. I know it's got to be a big number. Positive 14, and that is frequency, 1 over seconds. Okay, so why did I want to do that? I wanted to do frequency so that I could then take this equation and solve for wavelength. So wavelength, and I'll move it up here where I've got a little bit more room. Taking this equation and solving for wavelength, wavelength is equal to C divided by frequency. I know my C is 3 times 10 to the 8th meters per second. I know that value, and I just figured out the frequency. So I will divide by 2.34 times 10 to the 14, 1 over seconds. That'll give it to me in meters, but this is asking for it in nanometers. So I say I don't want nanometers. Okay, I don't want meters. I do want nanometers. Cancel my meters. I want nanometers. Okay, 1 nanometer is 10 to the minus 9 meters. And let's make sure everything's canceling well. The meters are going away. The nanometers are remaining behind. And that is where the number to 3 significant figures, and that's why I've got a 0 there at the end, is nanometers. You might have chosen to write it as 1.28 times 10 to the 3rd nanometers. All right, that fits in there, doesn't it? Okay, so when you know the transition of an electron from a high state to a low state, you know it's going to emit a photon of light, where the energy of that photon of light is exactly equal to the change in energy of the electron. You have to do all of this to get the energy transition of the electron. Once you know the energy of the photon, which we had, we can then get the frequency of that photon and the wavelength of that photon.